So in this video we're going to find the general solution for a first order linear differential equation. So we have the first order linear differential equation given by x y prime plus 2y equals cosine x. Remember, a first order linear differential equation is going to have the form ax y prime plus b of x y equals some function of x. And so this meets that form with a of x equal x, b of x equals 2, and c of x equals cosine x. So the solution process that we went through in the previous video for solving a first order linear differential equation is to first get the leading coefficient on the y prime term to be 1. So we do that by dividing through by x. So we divide everything by x, which then simplifies this to y prime plus 2 over xy equals 1 over x times the cosine of x. And then this now is in the form that we saw in the previous video, y prime plus p of x y equals q of x. And remember, we'll make the integrating factor by letting u equal e to the antiderivative of the p of x term integrated with respect to dx. So our p of x in this case is 2 over x. So our integrating factor is going to be u equals e to the antiderivative of 2 over x dx. So again, our p of x is equal to 2 over x. And so we need to integrate 2 over x dx, any antiderivative. So I know that we get a constant of integration when we do an indefinite integral, but we'll just let our constant of integration be 0. So we'll take the simplest possible antiderivative we can get. So we're going to get e to the 2 times the antiderivative of 1 over x is going to be the natural log of x. And again, we don't need the plus c. We're just going to let c equal 0 because any antiderivative of 2 over x will work. And I don't need the absolute value bars on the x because we're restricting x to be larger than 0. So you don't need to worry about the absolute value. And then what we want to recognize is that by log properties, that this can be rewritten as e to the natural log of x squared. And e to the natural log of x squared, because e and log base e are inverse functions, we just get x squared out of this. So this is our integrating factor u. And then the technique is to multiply both sides of our equation by the integrating factor u. So we multiply the left-hand side by x squared, and we multiply the right-hand side by x squared. So if we do that, we're going to get x squared times 1 over x is x times the cosine of x. And then we're going to get x squared y plus x times 2 over x will simplify to 2x times y. And the idea is behind this technique is that if we multiply both sides by the integrating factor, if we don't make a mistake in the calculation of the integrating factor, what we wind up with here should just be the u. It should be the u, whatever your integrating factor is, times y. It should wind up being uy prime. So our integrating factor was x squared, and then times y, the derivative of that, if we haven't made an error, x squared times y, u times y prime, the derivative of this should be what we see on the previous line. So to check our work, it's simply a matter of taking the derivative of this. So x squared times y prime, this is a product rule. X squared times the derivative of y. Oop, there's a mistake there on my distribution. I dropped my prime symbol. That's why we do a check on work. X squared times y prime should be x squared y prime. So x squared times y prime plus, and then it would be the derivative of x squared, which is 2x times y, just applying the product rule. So it checks. And once this is a derivative, I can undo the derivative by integrating it. So we'll integrate both sides with respect to x, and when we integrate we get a constant of integration, And when we integrate a derivative, we just get back what we started with. The integration and derivation will cancel each other essentially. So we'll get x squared y equals, and here I have an x times a cosine, so I can either go to a table of integrals or I could use integration by parts. So I'm going to go u sub 1 to distinguish this u from the u I have here. So I'll let u sub 1 equal the x, which means u1 prime will just equal 1, and that's going to mean that I need to let v prime equal the cosine of x, which means v needs to be equal to the sine function because the derivative of the sine is cosine. So integration by parts, I get the u times the v, I get x times sine x right here, x times sine of x, minus the integral of u prime v, so 1 times sine x is sine x, and this is a dx plus a constant of integration, so we get x squared y equals x sine of x, and the antiderivative of sine is going to be minus cosine, and that minus will combine with the subtraction to give me a plus cosine of x. Check on work would be to take the derivative of plus cosine and make sure we get a minus sine out of it, and then we get plus our constant of integration, and then we just need to get y by itself. So we can think of this two ways. I can think of it as needing to multiply both sides by 1 over x squared or divide both sides by x squared. But if we remember, 1 over x squared is the same as x to the negative 2. So to divide both sides by x squared or multiply by 1 over x squared, I can simply multiply both sides by x to the negative 2. Which I think is a little bit more convenient form to use in this case. So x to the negative 2 times x squared is just 1. Remember, multiply same like bases. We add the exponents, so negative 2 plus 2 is 0. X to the 0 for x greater than 0 is 1. And then I can distribute the x to the negative 2 into the parentheses. So x to the first times x to the negative 2 will be x to the negative first power times the sine of x plus x to the negative second power times the cosine of x plus c times x to the negative second power right there. So this is the general solution, and we call it the general solution when our solution still has the constant or constants of integration in it, when we don't have initial conditions that allows us to solve for those.